Thus, the use of external memory consumes many of the port pins, leaving only port 1 and port 3 for general input-output. Now we'll see the external memory access cycle. That is how the ROM is read, as well the content of RAM are read by the 8051 microcontroller. Before that, we'll again see this interfacing diagram of the external memory to 8051. As shown here, port 0 is time multiplexed. That is, it first provides the lower byte of the address and then acts as a bidirectional data bus to write or read a byte of memory data. Here it is shown, the port 0 pins, they are 87 down to 80. AD stands for address and data. Those are provided to both EEPROM as well RAM. During the first memory cycle, they act as the address bus, address lines, and during the second cycle, they act as the data lines. They carry the lower byte of the data. Port 2 provides the high byte of the memory address during entire memory cycle. Port 2 is dedicated for the address purpose only, and it is nothing but the high, it carries the high byte of the memory address. The lower address byte is latched by the ALE pulse, which enables the 373 data latch. We know the time multiplexing is carried out for the port 0 lines, and the separation between the address and data is carried out by the signal, which is nothing but the address latch enable. So during the first cycle itself, the address latch enable gets the status high so that the latch is transparent and the address is passed on to the output side of the latch, and the same information is provided to the EEPROM as well the RAM. The timing associated with the external memory access cycle is as shown in this figure. You can observe the ALE goes high during the first cycle, and as the ALE goes high, it carries out the separation between the time, the address and the data. The port 0 consists of the address information A0 to A7 during the first cycle, and it contains the information which is nothing but data, that is D0 to D7 in the second cycle. For the external ROM access, the PSEN bar pin goes low to enable the ROM. For ROM, it is read-only memory, so there is no question of writing to it. So only read operation is performed, and during second cycle, the PSEN bar signal goes low, so and with respect to which the content of the ROM are read. For RAM, there are both the operations possible, that is read and write. So the read bar or write bar pin goes low for enabling the data flow between the RAM and the data bus. If it is the read operation with respect to RAM, then the read bar signal is activated, and if it is writing operation with respect to ROM, with respect to RAM, then the write bar signal is activated. This is the external memory access cycle for 8051 with respect to both ROM and RAM. External memory addressing is shown here for referring to the ROM using the PSEN bar signal and accessing RAM using the read bar and write bar signal. Very important is the ALE signal, which carries out the separation between the address and data bus. During the first cycle, address is latched by the 373 type of latch, and the address information is available at the output of it. Rather, it is available for the entire read or write machine cycle. Now we'll discuss the interrupt structure and response for the 8051 microcontroller. Interrupts force the program to call a subroutine. They take the processor time only when action by the program is needed. Most applications of microcontroller involve responding to events quickly enough to control the environment that generates the events. Interrupts are often the only way in which real-time programming can be done successfully. Any interrupt causes 8051 to perform a hardware call to an interrupt handling subroutine that is located at predetermined absolute address in the program memory. There are 5 interrupts in the 8051 microcontroller structure. 3 of them are internal and 2 are external. The 3 internal interrupts are timer flag interrupts and serial port interrupts, while the remaining 2 external interrupts are INT 0 bar and INT 1 bar. Very first we'll see the timer flag interrupt. When the timer or counter flag overflows, the corresponding timer flag is set to 1. There are 2 timer flags, timer TF0, which is the flag associated with timer 0, and TF1, which is the flag associated with the timer 1. This flag is cleared to 0 when the resulting interrupt generates a program call to the appropriate timer subroutine in the memory. So it is not required by the user to disable these flags. The third internal interrupt is nothing but the serial port interrupt. If the data byte is received, an interrupt bit RI is set to 1 in the SCON register. When the data byte has been transmitted on the interrupt, an interrupt bit TI is set to 1 in the SCON register. These 2 bits, that is RI and TI, they are all together to provide a single interrupt to the processor, which is known as serial port interrupt. These bits are not cleared when the interrupt generated program call is made by the processor. The program that handles serial data communication must reset RI or TI to 0 to enable the next data communication operation. So far we discussed about the internal interrupts of 8051. The 2 internal interrupts are associated with the timer counter operation and one is associated with the serial port operation. Now we will discuss the external interrupts associated with the 8051. Pins INT 0 bar and INT 1 bar are used by external circuitry inputs. Pins INT 0 bar and INT 1 bar are used by the external circuitry. Inputs on these pins can set the interrupt flags I0 and I1, which are there in the TCON register. They are generated by 2 ways. First is when INT 0 bar and INT 1 bar pin signal reaches low level, or the another way is when high to low transition takes place on the pins INT 0 bar and INT 1 bar. One of these ways is decided by the bits IT0 and IT1, which are there in the TCON register. When these bits are cleared to 0, then the external interrupts are low level triggered. That is, when INT 0 bar and INT 1 bar pins signal reaches a low level, at that time the interrupt is activated. When these bits IT0 and IT1 they are set to 1, these external interrupts are negative age triggered inputs. That is, they are activated only when there is a high to low transition on the input pins INT 0 bar and INT 1 bar. Flags I0 and I1 will be reset when the transition generated interrupt is accepted by the processor and the interrupt subroutine is assessed. But it is the responsibility of the system designer and the programmer to reset any level triggered interrupt inputs when they are serviced by the program. This is the another distinction between the level triggered external interrupt inputs and the age triggered external interrupt inputs. The external circuit must remove the low level before the RETI instruction is executed. RETI instruction is nothing but return from interrupt, and it is written at the end of the interrupt service routine. Before this instruction is executed, the external circuit must remove the low level. Otherwise, the low level will result in an immediate interrupt after RETI from the same source. This drawback is not present there in the age triggered external interrupt inputs.